this class, we will continue on the properties of wave. Properties of wave. Properties of wave. Because wave is what you will use to probe the nano part later on. That's why the technology part, we focus on wave. Later, when we deal with nano, especially the tool, then it's easy for you lah. So I will not repeat again why we use electron, why we use X-ray in order to use certain tools for Bionanotechnology. So we finish this wave part under the technology, and then only then maybe next class we go for nano. Okay. So properties of wave, we have learned in the previous class that there are many properties of wave. One of the properties of the wave is absorption. Absorption is can undergo absorption, transmission, what else? Reflection, and then what else? Diffraction, refraction. It can be what else? Scattered. I mean, normally we call it dispersion, and then you can also, the wave also, another properties of wave is interference. So this, in the last class, in the previous two class, we more or less learn about the absorption, and we touch a little bit about interference. Interference is basically when two waves collide, it's either destructive or constructive. If you have two waves like this, add together, you get something bigger. So this is constructive interference. It's only happen for wave. It's unique for wave. If you have like a particle like this, if you try to collide it, it just bounce back. Okay. But for wave, it's either destructive. For example, if this is what we call up and this is down, if they collide, if the wave collide, then it disappears. It's like destructive lah. It's like you have a water ripple. If the water ripple in one phase, this is what we call in phase lah, up and up, then you get a bigger wave lah. If you have something like this and then you meet something that is the opposite side, the out of phase, we call it out of phase. This is what we call out of phase. Then the wave will be what we call interfere destructively. We call it interfere destructively. This thing, we call it interference. This interference. This is constructive, and this is destructive. The use of this, we will use this phenomena, interference, especially when we deal with the SRD later on. SRD is one of the tools under nano where we try to see the position of the atom inside the molecule. For example, inside this, you know there are atoms, right? Inside this pen, there are, the pen is not really good lah because it's metal. Inside this, inside this cap, it's made of polymer, right? It's made of polymer, right? So polymer, we know there are a lot of structure you can make this. For example, you know that glucose, sugar, the polymer base is something like this, whatever like this, and then something like this, OH, and then you have another long. So this is basically the, not glucose, cellulose lah. This is glucose. So when you make chain, you combine chain upon chain, you get a cellulose, which is made of this paper lah. Okay. So about this cap, they also have their own structure, but not like this lah, because this is not glucose or cellulose. It's something else. So it has its own structure lah. So to know whether it's hydroxyl, this hydroxyl group, ester group, whatsoever, to know that you can use chemical tools, for example FTIR, to do that. But to know the exact position, how this thing occur in space, then you cannot use a chemical, what I call chemical-based tool. That's where the SRD come into place lah. For example, people know that for the DNA, you have this, what we call, here you have the A and G, and then this CT, A for adenine, G for guanine, T for what? Tyrosine, thymine, C for cytosine. Cytosine. This thing, the scientists know long time ago. What is this A? What is this G? What is this C? What is this T? But they don't know how this, in terms of structure, I mean, in 3D space, how that's combined. So to know that, the scientists know about this double helix structure based on SRD. So SRD, X-ray, diffraction. So X-ray, we learn about the wave, is a wave, type of wave, X-ray. And D is basically diffraction lah, diffraction. And diffraction is basically one of the properties of the wave, okay? So that's why we study wave first. So just give you the idea. Later on, when we deal with the SRD, we're coming back here, but I will not touch about this, what is diffraction and so on. So that's basically the reason why we study wave, like a 3 class like that, because it's a basis for all the tools later on. Okay, we studied absorption before. Transmission is basically when you see something transparent, the wave just go through, so that's transmission, so no need to study much about that. But what we will focus is this: absorption, reflection, diffraction, refraction. Interference also we will focus, but later lah during the SRD, although you also know a little bit about interference, but this 1, 2, 3, 4 is the one that we will focus. Okay, so about absorption, you know in the previous class that when you shine a light or electromagnetic wave to certain object, it can absorb the energy, because light, even light, that gives you energy. So you have the what we call the atom, and then you have this electron around the electron, and then you give it the electromagnetic spectrum or whatever, light or photon. So you basically giving the energy to this atom. Imagine this is the atom, whatever. So this energy, some energy is enough to kick the the electron up to the higher energy level. It's enough, this wave is enough to kick this thing to certain energy level. Okay, so that's this thing what we call, this process what we call this? This what we call excitation. This thing we call excitation. Excitation. Okay, and then this what we call this energy that is excited will go to the high energy level, and then it's not stable there, and then it goes down back. So it can go here, or it can go straight to here. But normally, so it can go this, or and then they go in step, or it can go one step only. So this what we call, from top to bottom, what we call this thing, what we call the process of the unstable electron on the high energy level goes back to the ground state. What we call that thing? The term. So that is their excitation. The excitation. So imagine this, the wave. The wave come. The wave come. So let me change the color lah. Now it's good to see. Let's see. So this is excitation. Okay, upon the excitation, it's like when you try to pull the spring. When you try to release, what happened? The spring goes back to the original state. So basically, when you release the spring, you release back the energy. In terms of spring, you release the kinetic energy. But in terms of this, when you de-excite, same thing happen like the spring lah. But here, it will release the exact amount of energy that it's absorbed. So for example, let's say it's absorbed X amount of energy, it will de-excite with certain amount of energy. So this certain energy, they can release back the wave lah. So this wave, whatever this emit back, it can be either you can see it or you cannot see it. So it can be either the emission, this is what we call emission of the photon or whatever. So this emission can be either you can see it or you cannot see it. If you can see it, then you see color lah. If you cannot see it, for example in UV, then you cannot see lah in the visible light. So this is what we call emission. So this excitation de-excitation happen because absorption. Absorption. Put this color lah. The reason why this happens is because of absorption of energy. Absorption of energy. So this absorption, excitation, de-excitation, and emission sort of like intercorrelate lah. Okay. Sometimes you don't see anything emit. It's not like you don't see. It's just you cannot see invisible light. Because it's like when you have a banknote. You know, you have the banknote. You have this 1 ringgit. And then you know that they are like what we call the fluorescent material inside this. If you put under the what we call under the light, remember light also is the electromagnetic spectrum. And then when it hit the banknote, when the light, for example, you have light here, when it's hit banknote, it's basically it's hitting it with the sort of energy. They have energy because if you look at the what we call this thing, even visible light have their own energy. Yeah. We learned before how to relate the frequency with the energy, right? In the previous class, we learned about the energy equivalent to Planck constant plus the frequency. So the higher the frequency, the higher the energy. So if you see the visible light, you can see the frequency is around roughly lah terahertz. So this terahertz, they carries with it its energy. So when you shine something with the light, that's why when you go in the morning, you go you wake up in the morning and you go under the sun, you feel energetic because the sun gives you energy. Not the sun lah, I mean God lah. But anyway, so even this, even the light here, it will sort of like if you have a banknote you put here. This constantly receive the energy from the light, from the visible light. But that energy is not enough to kick this to higher energy level. That's why you don't see anything. But if you use UV, let's say you use UV, and then you try to shine to this, you can see fluorescence because the UV have higher energy. You see UV here is more dense and higher frequency, and it's enough energy to kick to what we call to higher energy level. So that is absorption, excitation, de-excitation, and emission. Okay. So so that is about absorption. There are one also, if you give too much energy also is a problem. If you give too much energy, let's say you have this thing, and then you have this thing, and then you have the electron, let's say the electron here, the electron here, the electron here, whatever electron, and then you give, let's say you give, instead of the UV or the light, you give the gamma ray. Let's say you give a gamma ray. Gamma ray. So gamma ray, as you can see, the frequency is much higher, meaning that it has higher energy. So if you give too much, then they are what we call this thing, the electron, especially the outermost electron, can be kicked out. Can be kicked out from the what we call from the atom itself. Okay. So this thing we call what? What we call this? This, the electron still maintained in the atom. Here is too much to the point that some electron, they receive the energy, but then it's too much to the point that the electron is kicked out from the atom. What we call this thing? Ionization. Ionization. So basically, you see, for example, let's say you have sodium neutral like this. And then when you get ionization, you get something like this. Okay, because plus here meaning that you diffusion of the electron, one electron. So you have this ionization lah. But this is happen during the solubilization of sodium lah. But when you irradiate atom, whatever, using the very high energy, very high frequency thing, then you can also sort of like boil this thing. You get this ionization to the point that the electron will kick off from the atom itself. So this is ionization. You left with the ion. Okay. Normally ion you see they are plus or minus like that. Okay. Something X plus. So that's ion. So this ionization. So that is one part. What else? Okay, I want to talk a little bit about this. Why why it's lit like this. It's not, as I said before, it doesn't go gradually. So this, why the orbit, why they are orbit, why they are like, although the correct one is a shell lah. You have the nucleus and then you have the shell of electron. Okay, why they are shell is because of quantization of the energy lah. The energy, you need to understand the energy. Let me talk a little bit about energy. Energy, because later on when we go to the nano, this thing happen. When we talk about energy, you don't view energy like this. Let's say you increase the energy, it doesn't go like this. It doesn't go sort of like gradually, continuously like this. But rather, it goes like this. It goes like what we call stair. Okay. So the energy cannot. So this is what quantum theory means, meaning that the energy is quantized. So the energy cannot be in the middle. Either, for example, when you walk on the stair, it's either you walk on the first stair or the second right. You cannot what you call? Pijak apa pijak? Step on the middle half of the stair, whatever. So you need either here or here. So the energy, even though normally we think energy is continuous, but actually it's basically not continuous. Even though like this, if you try to, even though you feel energy like this, keep increasing like that, but if you try to magnify this thing, you can see something like this also. It's quantized. So quantized, when you see, it's like when you see the light lah. You see the light like this coming to you continuous, right? You don't see like it's come to you like a packet of light, right? It's like continuous. This is you. You don't see this lamp. You don't see the light coming like this, right? You see the light coming like this, right? More like continuous. But in reality, if let's say you can see, because the light is so small, I mean the what you call the energy for the light, each packet of light is so small, so that's why you see continuous. But if you can sort of like magnify, not magnify, meaning that if you can see the light to the basis, the light is basically coming to you like this. A packet inside, in packet. So this packet of light is what we call quantization of energy. This thing, the knowledge of quantization of the energy is what make quantum theory born. Okay, because previously this what we call this Bohr model of the atom, they know it, but they cannot they cannot explain why this thing, why this what we call certain when you give certain energy, it goes to the another energy level. Okay, so that is a quantization of the energy lah. Okay. So now we see that the absorption related to excitation, de-excitation, and emission. And if you have this, you have ionization, and you also learn about the energy is what we call is quantized. So the idea is like it's like you energy is like step of stair lah. It's not like continuous like this. Okay. So this quantization of energy is what make the what we call the you can see the orbital in the electron. So the electron if you remember in organic chemistry, they have this S shell, like the sphere, and then also you have the P shell, SPDF, SP, and then D is like what? D is SPDF. D is how? 4. I remember about something like this lah, whatever lah. But you can see this thing, the orbital, this is the true orbital lah. It's not like this, but the idea is same. For example, this S orbital, the lowest orbital here, they are separate than the next energy level. They're not like in one gradual thing. It's separate. The reason for this is because have something to do with the standing wave. the electron. The electron, in order to what we call, to view this thing, because the electron doesn't have this orbit actually. It's basically, they are reside in this orbital, meaning that you can find, when you say p orbital, meaning that you have, for example, you can find the electron most likely here. Most likely here. It's about probability. It's not about what we call discrete anymore. It's not about exact. When you deal with the quantum, it's about probability. Okay. So this thing, the reason why it has its own shape, this shape S, and then P like this, D like this, F something like different lah. The reason why they have this shape is because people view this electron not as a particle, but rather as a wave. You see the electron, we can view electron as a particle and also as a wave. Okay, but in order to satisfy this model, you need to view the electron as a wave. Okay, and we know for the electron, same like we do in the last class, the electron, if it did, let's say this nucleus of the atom, if the electron behave like a wave, then it will look like this, something like this, okay. The electron move, something like this lah. If it's the electron, we regard this electron as a wave lah. So the reason why they have like what we call energy is quantized is because of these wave properties. Remember in the last class we learned about the standing wave when siapa? Kasgina namanya. Nama famous siapa? Erika and siapa? Rifdi they do this thing. We see that there are only certain, when you feed a certain energy, only the standing wave will occur. For example, this is Rifdi, this is Erika in the last class. So either you get something like this, I don't remember lah, something like this, okay. So this standing wave, you refer in the previous class, and only after Rifdi give exact frequency, then you get something like this. Meaning that instead of one note, you have this 1 and 2 note. So this is something like this lah, something like this in the middle. Okay. So basically, you see that you have like 2 note here, 2 note in the middle, giving you a 3 half wave. We call it half wave. This is 1, this is 2 half wave. The second one, you have 1 and 2 and 3. So this kind of quantization also, because you cannot get in the middle. You either get the 1, 2, and then the next one is 3, and then the next one is 4, and then 5. You cannot have in the middle. So that seems like the stair lah. You cannot have this, for example, this one, stair number 1, stair number 2, stair number 3, 4, 5. You cannot have anything in the middle, same like this. So this, if we bring this concept to the electron, you can see here, the electron here, let's say you have 4, what we call 4 loop, and then the next energy level must be 5, must be like this, must be something like this, must be like this, because you know one of the properties of the wave is that it's destructive. Okay, so if you have something in the middle, between this and this, what will happen is something like this. If you have something in the middle, between 4 and 5, 1, 2, 3, 4, 5, okay. 1, 2, 3, 4, let's say you want in the middle. So the wave will sort of like destructively interfere because of not in phase. It's like when you have like when you want to make a round shape using the paper clip, you have one paper clip. Let's say you have 4 paper clip, 1, 2, 3, 4 paper clip, and then you make like a circle. In order to make another level, you need to add the full paper clip, right? 1, 2, 3, 4, 5, in order to get a full circle again. So you cannot make, because you only have this paper clip as what we call the building block. So you cannot have in the half or whatever. You need to have a full one in order to complete this thing. Same like the wave, but the wave have their unique properties of interference. This is one of the unique properties of interference. When you are not in phase, meaning that here, up, you get big. If you have like this, not in phase, it will be destructive. So that's the reason why the energy level in an atom have their own level. It's not like continuous. You need to go either here or here. You cannot go in the middle. So that's what it means. The electron can be either in this, the lower orbit, or the second orbit. Electron cannot be in the middle here. So that's what does it mean by quantization of energy. So that is, and the reason for that is because of this standing wave of the electron. If the standing wave interfere like this, out of phase, then you get nothing lah. You get nothing. You get no wave lah. Until it reach this exact what we call it accept this enough energy level, then we got this 5 lah. So you have 4, this 5, never 4.2, 4.3 like that. So this is basically the idea of quantization of energy, and also why you see the orbital occur. Why they are orbit? Why not it's just like electron move around like that? They must be orbit because of this, the definite ni lah. Okay. So what is the example of this? Okay, we talk about this because this concept here is important. This concept, even though you see how this thing relate with Bionano, right? How this talking about the electron wave relate with Bionano? This thing is the basis of electron microscopy, which is the reason why we can see nano. Because if let's say the electron microscopy, the name itself, electron, meaning they use electron to see. Normal microscope use light, right? So how come you have something like normal microscope here, using light, and then you want to use what we call electron to see stuff? Because light, you know, is wave, sort of like wave lah, even though light is also particle also, but for this purpose, we think like the light that we use to look at the small object is a wave. So now how this and this correlate? Because electron, normally people think electron as a particle. It's a particle. But because of this, then we can say that yes, electron can also be wave. And the reason why they use electron, because the electron have a very small wavelength than the light, so that we can resolve the small object. Because in order to see small object, you need that object to be bigger than the source of light. For example, let's say I have what we call, I have hair. Hair, right? If I put on my table here, and then if I want to take with my hand, imagine this, my hand is like a wave. So it's pretty difficult, right? Pretty difficult for me to take this hair. It's not difficult lah because it's a little bit big. But if I have something like this, it's much easier, right? So it shows that if you want to see, I mean this, I want to, what you call, touch or whatever lah, but same idea lah. If let's say the wavelength, let's say imagine this one wavelength, if I want to, if the thing is bigger, it's much easier to take lah. But if something is too small, then it's not easy to, what we call, to take up, to pick it up. So basically that is basically resolution lah. So in order to see something small, the object must be bigger than the wavelength of whatever source that illuminate. In terms of light, here, you can see bacteria here under the microscope here, microscope, visible light. You can use a visible normal optical microscope to see the bacteria, because bacteria is bigger than the visible light, the wavelength. You see the wavelength meter, so visible light is around micron, right? Micron. So bacteria also in micron. So that's why you can see. It's bigger, it's easy. But if you want to see the molecule, like for example atom, you cannot use a normal microscope, you need to use electron. Why people cannot use the X-ray? Why people don't use X-ray? Because if you think, why people need to use electron? Why don't they use just X-ray? Because X-ray also have a smaller what you call, smaller wavelength. Why they don't use X-ray? Why they don't use gamma? But let's say you want to see the atomic structure of this metal. You don't care about ionization at all, right? I mean, yeah, you care a little bit, but yeah, that's one way lah. But it's not like when you analyze something, for example, when you, let's say you have petri dish, right? You want to sterilize petri dish, you use gamma. When you shine the gamma to the petri dish, it's not like petri dish will disappear, right? The petri dish is still there. Maybe the ionization will happen, but it's not like to the point that it will degrade the entire petri dish. Because the ionization, when you try to shine the gamma ray to the petri dish, you ionize the DNA molecule of the bacteria. Because it's easily ionized, that why bacteria die or whatever lah, virus die. But the plastic itself, the atom inside the plastic, because plastic made of atom, right? The atom in the plastic and also the atom inside the bacteria body is different. So maybe the atom inside the bacteria body is easily ionized. So that's why they mutate and they die. But for the plastic itself, it stays like that because you shine the gamma ray to the what we call, to the plastic petri dish. It's still there. It's not like it will disappear. So meaning that we can still sort of like use gamma ray for that. But the reason why people don't use this gamma, even though gamma have what we call smaller wavelength, is because, let's say, if I put here, let's say why not people use, instead of this, they use gamma. Why it doesn't use is because the electron here, electron is charged, right? Charged particle. Electron here is charged particle. Electron have charge. When you want to see something, you want to focus. For example, you want to use light. In order to make it bigger, you need to focus the light. That's why in the microscope you have this what you call lens. The lens something like this, right? Something like this, and then the light come in. The light come in, and then the light will bend and focus something like somehow like this lah. So you need to have something that you can focus on. Something focus on. Electron, they have charge negatively charged. Because of negatively charged, you can sort of like control it using the electromagnet. You can sort of like control the movement of the charge, bend here, bend there, using the electromagnet. And this allow focusing to happen. But when you use gamma, you cannot control. It's just like that. I mean, it's very, very difficult to focus gamma. So that's why people use electron. Not because gamma cannot be used. It's because gamma is hard to focus. When you hard to focus, then you cannot really see lah. I mean, you cannot really go deeper and deeper, magnify deeper and deeper. So that's one of the reasons why the electron. But the basis here, the reason why electron microscopy work is because the electron itself can what we call? The electron, what we call? Behave like a wave. Okay? So in electron microscopy, you have this electron gun. Electron gun here. So it beam up the beam. They provide the beam of electron, and this beam of electron, they have this wave, and the wave is smaller than the whatever object they want to see, and then due to that, they can resolve the object. So that's basically why people use electron lah. So that's one thing. So actually, if you look here, all of this, when you use electron microscope, they have a lot of things to do with all these properties of wave. When you use electron microscope, you deal with the diffraction. For example, this electromagnetic is basically sort of like diffract the thing, control this thing. And also you also deal with the reflection, absorption, interference a little bit lah. Okay, so we stop here for a while. We put this atom. Okay, so now that's about electron microscope. So okay now? Why people use electron for electron microscope is because electron give a smaller wave. And why electron have wave is because of this. The proposal here, because now it's easy because we are taking things for granted. People already done it for us. But imagine at that time when people don't know anything about electron, because long time ago there are no microscope like powerful like this. Before the electron microscope can be fabricated, they need to know this first. But for the first, at that time they don't know whether this electron is wave or particle and so on. So this basically the idea of this electron, what we call, give off the wave. Is basically the person that do that is basically, the name is de Broglie, the French de Broglie. So in fact this, they call it de Broglie wave, de Broglie wave. Okay, but basically we know this standing wave lah, normal standing wave. So this de Broglie, when they write this in his PhD thesis lah. Okay, they propose this in his PhD thesis, and this is the only person that got Nobel Prize based on PhD thesis. Okay, so they write PhD thesis, and then the examiner they give to Einstein, and then they say, oh, this is very revolutionary, and then they got Nobel Prize. So his age that time is 24. Okay, 24. Doing PhD, get Nobel Prize. Yeah. Okay, 24, what you do? Anyway, so that's the thing. So this also telling that, this concept also telling that that everything have a wave property, because everything is made of atom, and atom have electron. So everything, if this is true, everything should emanate the wave, right? For example, let's say I have this tennis ball. This also emanate the wave. Okay, but the wave is too small. So let me padam. Okay, let me padam. Yep. Okay, let me close this. Okay. Okay, because of this, people propose that everything should have a wave. In fact, that's true lah. So we know before that this energy here, energy equal to F. There also for this de Broglie part. So they equate the lambda, the wavelength is basically the H divide the momentum. In order to know the wavelength, because in order for them to use this for the electron microscope, they need to know how big is the wave itself. So what I call the formula they use is this lah. Don't need to know how to derive it, but this is the formula. The wave, and then this is the Planck constant. We learned in the last class, Planck constant here. And then this is momentum. So meaning that if I have this, let's say I have this ball, and I try to, tennis ball, and I try to short of light, because momentum is basically mass time velocity. This is momentum. Momentum. This is Planck constant. Planck constant. So basically, if I have a ball like this and I try to sort of like throw it very fast, let's say as fast as the speed of bullet, 330 meter per second, and this tennis ball, let's say 200 gram. Okay, so using this de Broglie equation, you will know what is the wave emanated from this tennis ball. So put here. So if you calculate lambda equal to H divided by mv, H we know is Planck constant, is 6.6 times 10 to the power of negative 34 joule per second, divided by mass is 0.2 kilogram, and then let's say, okay, mass kilogram, and then this is 330 meter per second. So let's say 330 meter per second. So you calculate that. I don't have the calculator. You want to see what is the wavelength if because I see that because of this, people assume that everything have a wave. Okay, so if I try to throw this so fast, this thing should be able to generate a wave. But how big is the wave? Okay, habis. You want to see that here? Siapa kasih 0.5? But anyone who give it, you get 0.5. Sorry? Siapa? 1 times? 1 times 10? Negative? 30? 35? 35. So tanya lagi. 0.5. Okay, it's okay. You need to what we call to be greedy, because the bonus mark come like that. So you need to be ready. So basically this basically when you do all these things you get meter lah. So this 1 times 10 to the power of negative 35 is so small. That's why you see it's like a particle, not as a wave. Okay, you cannot see because if this is negative 35 is more than what? It's like femto, million nano. So it's so small, that's why now you see it as an object, not as a wave. But let's see the electron, because we talk about electron. So electron, let's say electron here. Let's say electron have the mass. Manalah saya tahu. Wait, electron, mass of electron. Mass of electron, because you need have mass. Mass of electron, mass of electron berapa? Mass of electron. Right, ada internet. Okay. Wait, this thing being here. So if you try to this, and let's say this electron move, let's say we don't go very fast lah, we go maybe what we call just like 2% of the speed of light. Speed of light. Okay, so the mass of electron is, I'm not a robot. I hate this. And then you get more, and then more, I don't know lah, siapa lah buat ni. Tak salah. Mana? Crosswalk, dah. Qualify. Insya-Allah. Okay. Okay, anyone do this, you get 1 mark because I didn't tell you. Because this is 0.5, this is 1 mark. Electron, that mass, 2% of the speed of light. What is the wavelength? Because this is the basis of the electron gun inside the electron microscopy. We want to see the electron to behave like a wave. This is Planck constant. 6 times 6, 6.6 times 10 to the power of negative 34. Electron move 2% of the speed of light. What is the wavelength? Because we want to see what is the wavelength of the electron so that it can be used to look at the small object. Ni 1 point. I don't give bonus mark often. If I think I want to give, I give. Yes, Hani. Hani pula. Rohani. Ya. 2? 2.96. 24965.6. Masih ni tengok. Alah, buat dalam ni scientific notation. Like this. Do something like this. Anyone? So Rohani void. You need to do in the scientific notation. That's why we learn about prefix, scientific notation and so on. Anyone? What is the wavelength of this? Of the electron that is moved so fast to the speed of 2% of speed of light. What is the wavelength? Anyone? Simple calculation only. Faster. If I write, then no more. 1, 2, 3, 4. Anyone?
1.208.
1, 2, times
10 to the power of
negative 10. Okay. So basically how apa siapa nama saya lupa lah. Inilah first time saya lupa nama saya punya ni. Ikhwan ke? Afiq ke? Apa benda nama? Asfar. Asfar. 6.6 times 10 to the power of negative 34 divide by that thing 9.1 times 10 to the power of negative 31 and then time 0.2 because 0.2 speed of light time with the speed of light you need to know lah 3000 3 times 10 to the power of x meter lah. So that's the thing. So Asfar ke? Nama Asfar 1.0. Okay. So you get this thing. If you look at this wavelength, you see this wavelength more or less the wavelength of the atom, because the atom, as I said, the hydrogen atom, the diameter for hydrogen atom is around angstrom, right? Angstrom is basically 10 to the power of negative 10. So meaning that if let's say you use this electron inside the electron microscope, because electron microscope is like this big, like this big. So let me show you electron microscope how it looks. Electron, apa benda tu? Electron microscope. Okay, so image. Okay, so you can see here, it's this big, this big, and I make it bigger lah. So our normal microscope like this, they use light only. You see the light coming, they use light. Okay, but the light is not small enough to resolve, like for example virus or atom. So they use electron microscope. So yeah, that is electron microscope. So basically on top of here, they are electric gun. They are, we call it emitter lah, electric gun. So basically, this electric gun, they beam the electron so fast. Okay, let's say it's at the speed of 2% of speed of light. So that speed of light, that the electron from top to go down, they give this wavelength. So because this wavelength is more or less similar to this, they will sort of like can resolve lah. They resolve the small object. So this thing, resolve or not, is depend on the diffraction, which we will learn later on lah. What is diffraction and so on. Okay, so just here I want to show you that why people use electron in electron microscopy, because it can give this small wavelength, which is enough to resolve small object. Because I just give you the idea about diffraction. Okay. Let's say I put here, just small idea. If let's say you are in the, let's say they are like, this is a C. Let's say this is C. This is C. Let's say this is C. This is C. C. Loud. C. C. Loud. So let's say you have a ripple here. You have a ripple here going down. Okay, let's say they are like a ripple, the C going down. Imagine now they are like a small stone here in the middle. If this stone is so small, then the C ripple just go through like that, right? But if let's say this stone is big, let's say this big, what happened? This thing will sort of like diffract, we call it diffract lah. Sort of like something become like this. Susah agak ni. Susah betul lah. It become like this. Something like this, and then suddenly it goes something like this, right? Something like this lah. It goes like something like this. If let's say, imagine now, tak payahlah ni. Another C, let's say another C in the side, so this C1, this C2, C number 1, C number 2, but this C, they have like very small ripple, and then suddenly it's met with what we call the same object like this. What do you think will happen? small ripple. So this we sort of cast a shadow, something like that. Something like that. Something like that lah. So this what we call the wavelength. This we call analogous. It's not analogous, it's actually wavelength lah, because we see, right, ripple. So this wavelength. This also wavelength lah, but this wavelength is bigger lah. This is wavelength, let's say wavelength A1. This is wavelength 2. Okay, you see the difference, when you use the smaller wavelength of whatever, and this wavelength hit the obstacle, anything, for example batu ke, apa ke, stone ke, this wavelength, if it's too small, the shadow, we call it shadow lah. This is what we call shadow region. This is shadow. This is what we call shadow region. Shadow region. The shadow region is sort of like a lot lah. I mean, it just go through. So it's like, I mean, logically lah. But if let's say the stone there is more or less the same size of the wavelength, you can see there are shadow region here, but over time it will merge again like this. Okay, so in order to see an object, tak cantik nanti keliru, shadow region. Shadow region. So in order to see the object, it's like when you have torchlight, and then I have torchlight here, and then I put Azam tidur. Azam sini. Azam kat sini. So you will see, nama you Azam Azam ke Azim? Azam Ha? Azam belakang Rifdi. Siapa? Azam Let's say this Azam Azam So you shine the light, it's like you shine the light and then you see the shadow at the back, right? This is shadow Shadow. So the light have very small wavelength very small lah wavelength. You have this what you call the Azam, and then you get shadow. So same principle when you want to see something, you see the shadow, you see because from the shadow you can get the what you call the outline of the body and so on. Okay, so if let's say you try to shine, let's say there are microbe here, you don't see a shadow because the microbe and the light no, if you have a virus here, even if you shine with light, you cannot see a shadow because it's like this. Alah, ada lagi satu lah. Alah, sorry lah saya ni. Tak apa, ada video kan. So, the third what you call, the third situation is that C3, when you have something very small in the middle, and then you have patutlah saya pegang ni. You have a very big ripple go down. So you see there are no shadow at all. If you have the obstacle, but what we call the wavelength, so this wavelength 3. So let's say this wavelength 3, this is wavelength 3. So for this, the wavelength is much bigger than the object. So the wavelength just go through and there are no shadow. It's like you go lah, you pergi dekat pond tu, you try buat tak batu tengah. Batu wavelength, let's say apa nama dia? Stone in C. Stone in C. Macam ni. Stone in C, diffraction. Something like that lah. Something mana? Tak jelas lah. Okay. Tak jelas lah, tak ada gambar ke. Obstacle, stone, whatever lah. But I think you get the idea lah. I mean, how this thing occur lah. Diffraction, this is what we call diffraction. The bending of the wave. This is what we call the bending of the wave. The bending of the wave, what I call the idea of diffraction, the term diffraction itself is basically diffraction. Diffraction is basically bending of wave bending of wave when it hit the obstacle, hit an obstacle, or when it go through aperture, meaning that hole lah. For example, like this, right? You see the wave coming to here, and then suddenly they are like the hole there, and then suddenly the wave sort of like mengembang apa? Expand. Okay, so this bending of the wave, what I show here is basically bending of the wave because when it hit the obstacle, this is one part. So this part, bending of the wave when it's hit the obstacle. When it go through aperture, okay, I think I can. Yeah, when it hit aperture, it's like this. When you have the aperture like this, and then you have the wave coming through. Let's say this, you have something like this, and then you have the wave, and the wave more or less the same size of the opening. So let's say this is wave. Okay, goes down. What will happen is that it become like this, right? Somehow it become like expand like that. Okay, so this what we call bending of the wave when it goes through the aperture. So the idea is that when the opening, this is what we call the opening. This is the opening. Let's say we give it D, and then this is the wave length pi. If the wavelength is more or less equal with the D, then you get the diffraction lah. Diffraction. I mean, very big diffraction. So that is basically the idea of diffraction. The bending of the wave when it goes through ni lah, through opening, or because this also bending, right? This also bending. So this diffraction, we call it diffract. We call it diffract. Okay. But if let's say the what we call if let's say this thing, okay, the second one, and then let's say the wave now is much smaller. It's much smaller. Very small, very small, very small, very small goes here. Nothing happen. It just nothing happen. It just go like that. It just diffract a little bit only here. But that's it. And just go like normal lah. So here when the wavelength is sort of like much smaller than D. So this is D, it's still D. This thing D, and this is a wavelength. This is wavelength. So when the what we call the wavelength is much smaller than ni, they are very less diffraction lah. We can say there are no diffraction lah. No diffraction. Okay. So this diffraction cause what? This diffraction thing, because they are not sharp shadow, it's bent, it cause blurry image. When you try to what we call look under the microscope, sometimes you see something blurry, right? That's because of diffraction lah. Diffraction. You see due to the diffraction ni lah. So this what happen when wave hit an object or wave go through the aperture. So it will diffract, it will bend. So diffraction cause wave to bend. Okay? Wave to bend. And normally we don't want this diffraction when we use a microscope because they give blurry image. Okay? Okay. Absorption, you learn as normal, it's just absorb. Diffraction is this. Diffraction is bending of the wave. Bending of the wave, diffraction. Wave bend. Okay, so that's diffraction. We will maybe go a little bit further later on when we talk about the SRD. Because SRD, the term SRD, the tools that we use to look at the small object, the term SRD itself X-ray diffraction. So we want to see why they use X-ray, why there are diffraction there. So we will learn about that later on, about diffraction. So for direction, for time being, enough for you to understand this. Diffraction is a bending of the wave when it hit the obstacle or it go through aperture. So what you need to know is that what happens if the wavelength is bigger or smaller than the obstacle, what happens if the wavelength bigger or smaller than the opening. So that's what you need to understand lah. So that is bending of the wave. What F cause the wave to bend? What else? What else cause wave to bend? You have absorption, transmission, reflection, diffraction, refraction, scatter, interference. What F can bend the wave? Huh? Sorry? Reflect. Okay. Oh yeah. Reflect is true. Reflect is bending of the wave. It's basically let me remove this thing. So you know the reflection is simply you know the what we call the law of refraction is like this. This is true for any wave. Sound wave, light wave, or whatever wave. So reflection is basically, let's say you have a planar surface, and then you have this what we call, let's say, the one plane, and then you try to reflect a wave from here. It will reflect something here lah. So this will be same lah. This theta 1, theta 2, it will be same lah. The ray of incident, this is incident, incidence. This is reflected lah, reflected. So for under the reflection, theta 1 equal to theta 2 lah. Ya ke? Betul lah? Betul lah? Yalah. Betul kan? Betul lah tu. So the what we call the theta for the incident will be equal to the theta of the reflection lah. So this is the reflection. So reflection, you know this when you see the what we call the mirror, right? Normal thing, right? But it's also occur when you see something object. For example, let's say I have this red cube. You see this red cube. Why? Why you see this red cube? Huh? You see this red cube because this red cube, the light here coming here, it absorb everything except red, and then it reflect the red. Same idea like this lah. But in this red cube, the light come here, and you know the light is made up from light. So you know the light made up from the electromagnetic spectrum, and we know the 7 rainbow is what? Roy G. Biff. Roy G. Biff. So this red, orange, yellow, green, blue, indigo, and then violet. Okay. So basically the red here, what does it mean? Red is basically it just have something like this. The orange have something more energetic than the red, and then the yellow is basically even more energetic than the red, and the green, it's more energetic, and the blue, you have more energetic. And that, and then penat lah. Then you got macam ni. And then violet, you have something more energetic lah. Meaning that the wavelength is become smaller and smaller. So you can see the red have the very high wavelength, and the blue or indigo have the very small wavelength. Meaning that when you have a small wavelength, meaning that it has high frequency. Meaning that it has high energy. That's why when we talk about the watching the phone or computer, it's about blue light, right? This is the reason lah, because blue light is energetic. It can affect the thing lah. So that's why people call blue light thing. So when the light, which is made of what we call a lot of spectrum, the thing coming from this thing, from the light, is basically a mixture of all these things. As if you see there are something like this, and then something, this is red, and then this is blue. They combine like that lah. Basically, it's coming to you something like this. So it's a mixture of the thing. So when it hit this thing, let's say you have this thing, what happens is that they absorb everything that is not red and reflect the red. Okay, so that's why you see red lah. You see red. So normally we have what we call complementary color here. Complementary color. Okay, so let me talk about here. So for example, what you see is basically the complementary color of what is absorbed. For example, if you see red, meaning that a lot of green is absorbed. If you see red, a lot of green is absorbed. Okay, but it's not just, this is just a guidance only lah. For example, when you see like a green, for example, when you see a green leaf, so from here green, meaning that the red is absorbed, right? The red is absorbed, meaning that everything coming here, and then it's reflect green only, and most red is absorbed. Most red is absorbed. Okay, so the way how you check this is by using your UV spectrophotometer. UV spectrophotometer. You have used this, right? So if let's say you take this leaf and then you grind it, you make like a smoothie, and then you put in the cuvette. You know, right? Everyone of you know cuvette, right? And if that spectrophotometer give the graph, how it will look like? How it will look like? It will look like, because if you try to put this into this absorbent, let's say this absorbance. So this is red, this is blue, in middle is green. How the graph will look like? How the graph will look like here? How the graph will look like? For the this thing, for the what you call? For the you put this thing, you grind, you put into cuvette. You put into cuvette, so you have something green inside the cuvette. And then you try to put into the spectrophotometer. What you will see? Huh? What you see? Macam mana? It will absorb, kalau if green, it will absorb red for sure, more or less. So meaning that for red here, they have like a absorption, because this absorption meaning that you have a peak here. Peak here. For green, it doesn't absorb, so meaning it will be something like this. And then for the green, they are quite special because it's also absorb the blue lah. Absorb the blue. So basically, you get something like this. Something like this. Okay, the absorption, let's see, green. So basically chlorophyll lah. Chlorophyll. UV vis. Chlorophyll UV vis. Okay, so you can see that. So you can see for chlorophyll, this is chlorophyll lah, thing inside the pigment inside the your leaf. So basically, it will absorb the blue part and also the red part, and then this green it doesn't absorb. That's why you see green. Okay, so in fact, this thing tell you that the object color is not the intrinsic properties. For example, you see this red, but actually it's not red. The object doesn't have color. The object doesn't have color, because if you are color blind, you will see this different color. You will see this green if you are color blind. Anyone see green here? You don't see green, eh? If you see green here, meaning that you are color blind. Okay. So the color is not the intrinsic properties of the object. If I close the lamp, it's pitch dark. This thing, I don't see anything like, because color is not the intrinsic properties of the ni lah. You remember when you go in the car, you go through a tunnel. Have you ever see your baju color? You see your shirt something different color, right? So meaning that your shirt color is because that color because it appear to you, but in reality object doesn't really have color lah. It have color because of the light. There are no light, there are no color lah. So that's the idea. So that have something to do with the reflection. That have something to do with the reflection lah, reflection. So this is also so we talk about light, and also it's also true for the sound lah. For the sound, if I talk here, it's reflect lah. Same idea like this lah, it's reflect. When the sound wave goes to the very smooth surface, it's reflect like that. But if let's say you don't want a reflection, in sound they call it echo lah, echo, reflect, echo. If you don't want the reflection, then you need to put something, the absorption, For example, let's say you have seen something like this, right? Something like this, right? For microphone. So this is not smooth lah. So it's absorb the echo lah. They absorb the echo. So when you talk here, it will not. It just absorb the echo from the side. It will absorb here, absorb here, absorb here. So that's why when you see go to YouTube, see any streamers in their room, they have like a black panel here, acoustic panel, because the material can absorb sound. So that's also under this sound lah. And then this reflection for the sound is useful for what we call when you for like the bat, kelawar, bat. So bat, they sort of like what we call give off the ultrasonic sound wave also to the cave, so that it can reflect back to itself, and then it can create a map lah. Same principle also when you do the ultrasound. If you are pregnant later on, they use ultrasound to sort of like to see whatever inside, because something that is dense body, for example the baby bones, they will reflect faster than the if you go, for example, this baby bone, this baby. So if you have this tummy, so this ultrasound device. So basically the ultrasound will sort of like this device will emit the ultrasound, and then when this wave hit the dense object, it will reflect back lah. So that's why you can see the structure of the baby and so on. But if you go through the what we call something that is less dense, for example blood or whatever, it just go through. So that's basically the use of the reflection lah, for sound, for the light, for this, sound for this. So the wave have many uses lah. In fact, the wave, knowing about the wave, let the scientists create a lot of technological tools to do this thing, sonar, whatever. So all that about wave lah. So we recap for today. So today what we learned about the properties of the wave. We recall about the absorption, and we recall about the excitation, how absorption relate to excitation, de-excitation, and also emission, and also what we call the ionization. And then we learn about the electron can behave like a wave, and because of these properties, you get the orbital. And because electron give off the wave, you can use it to inside the electron microscope, and also you learn also why we don't use X-ray for electron microscope, because electron is charged, so you can sort of like play around with it, focus it, and then we learn about this thing, diffraction. The idea of diffraction we go in detail later on, but this is the idea of diffraction, the bending of the wave. Bending of the wave when it's hit the obstacle and go through aperture. You just make sure you know what is the relationship between the wavelength size and also the size of the obstacle or opening. They have some relationship. So diffraction is basically bending of the wave like this. And then we also talk about the bending of the wave due to reflection. Reflection also the bending of the wave. We see how this can be used, meaning that how this manifests when you see something, for example the red thing, you see something, this is because of absorption, we learned before absorption, and also reflection. In this case, when we talk about absorption, they are like, when we talk about absorption before, they have what we call excitation and de-excitation kan. Some de-excitation emit light, but when you see object doesn't really emit something. What you see is reflection rather than emission of the light due to the de-excitation. Okay, the lamp excite and emit light, but this, when you see the object, is more like reflection to you. It's not about emission, because we talk about absorption closely related to the excitation, de-excitation, and emission, right? But in this case, when you see the object, normal object doesn't emit light or whatever, so it's more like reflection. So that's the difference between something like the glowing, something like what we call the lamp, and this thing. Object doesn't emit light, it just reflects light. Okay, and also we learn about how this reflection also true to the wave sound wave. We talk about the use of that, the bed, the what we call this ultrasound for the baby, and we also learn about this different light. They have what we call wavelength and so on. So basically that's it for today about the properties of the wave. And next class we maybe go a little bit more on the refraction part, and then we go to the nano. Okay, so that's it for today.